Welcome to Underactuated Robotics. Fall 2015. It's cut off a little bit, but I got the year right, I think, yeah. I'm excited to have you in the class here. So let me start off by introducing Robin, who's right here, and Tuan. They are going to be amazing TAs. They are most recently part of the DARPA Robotics Challenge team, so if you have any questions about that kind of stuff, you can ask them. They're also incredibly good at the software back end of the course, and they know all the topics extremely well. They're going to be an incredible resource for you. Let me say that the course website here, we're going to use MITx to host it because it actually worked pretty well last time. We'll have software problem sets that we can grade online. There's an edX version of the course that'll run in parallel, but shouldn't affect you in any way. And if you've done an MITx thing before, the URLs are obnoxious, so we get a tiny URL for you. MIT-underactuated. So I've put everything up on we're not going to hand out anything in the class. The course policies are up there, the schedule's up there, the syllabus is up there, everything's right there. The course notes are also up there. I started writing the course notes in HTML5 raw, and so my favorite way to read them is just as a website. If you guys want PDFs, we can generate PDFs, but it's better to get the raw content because we've got videos in line and animations you can click on and stuff like that. I think it's the future. We'll see. You guys might, if you tell me you hate it, then maybe it's not the future and I'll change. But tell me what you think about that. Okay, so the goal for today is to bring, I know people come in from, one of the best things about this course is that people come in from a lot of different areas. I love that. I think that's the role that this course should play, is to bring everybody together and talk about dynamics. And I got to try to convince you today why dynamics is really important if you care about robotics, pretty much any area of robotics. Even if you consider yourself a computer science roboticist and I do learning or something like this, you should still care about dynamics, okay? And that's my goal today, is to convince you of that. I'll do that by telling you a little bit about my background, the background of robots at MIT here, and the motivation behind that. And then we'll get into some of the definitions to bring everybody into the sort of in the same place in terms of I want to define what underactuated is, since maybe a lot of you don't know. And then we'll talk about a couple of the relevant pieces, sort of introductory material. I want to end the course by telling you end the lecture today by telling you what's going to happen for the rest of the course. So I'll give you a kind of a quick sketch of what you're going to see over the rest of the semester. So let me start by telling you a bit about how I got started in dynamic robots and underactuated robotics. So I got to MIT in 99, and I guess in 2000, January 2000 is when I came as a grad student first. At the time, there was something called the Leg Laboratory. It was in the basement of NE43. It was a great place. You could go in, you could look up in the ceiling and see robots from years past hanging from the ceiling. Many of them are in the MIT Museum now. But MIT has a great history in making dynamic robots, right? So part of that history is the robots built by Mark Raybert. This was done in the early 80s. He started making these pogo stick-like robots that were hopping around, which at the time, this was at a time where most robots were moving in an extremely static way. So robots were shifting their center of mass into their single foot. They were moving at sort of glacial speeds if they had legs at all. And Mark came around and started making these hopping robots that were just throwing themselves through the air, right? And he argued pretty convincingly that you could think about pogo stick legs, the articulated legs of a human are sort of, you capture a lot of the essence of that if you think about a pogo stick robot. And these robots, the one that just passed had the land speed record for a long time for a bipedal robot. It's recently been broken. They were doing flips. This is incredibly impressive, right? So I was actually in the Leg Lab the day that Mark came back. Mark left MIT to start a company. I'll let you see this one too, right off the treadmill. And then he's got quadrupeds that were hopping around. This is in '84, he published papers on this. how beautiful that looks, right? Incredible. So I was actually hanging out in the basement in the leg lab with those guys when Gil Pratt was running the leg lab at the time, when I arrived as a grad student. And one day Mark, who had left to start a company and do simulation, dynamic simulation, he came back and he sort of looked at the treadmill, that same treadmill that you saw in the video over in the corner. He says, "You guys using that? We're thinking about doing robots again at our company," and that's turned into Boston Dynamics, which you might well know now. So I was also, when we were working on walking robots at the leg lab, there was this sort of shocking moment in history when, in 1997, Honda told the world, guess what, we've actually been working on walking robots for a pretty long time. It was something like 20 years of research behind the scenes that they'd been doing without telling anybody, and it culminated in this incredible demonstration with, at the time it was called PR2, it was not PR2, it's just P2, thank you. This was P2 that came out, okay. And they just announced to the world, oh, by the way, we've been doing walking robots behind the scenes, right? And the jaws dropped at the leg lab. It was quite a surprise to see a pretty dynamic gait out of these robots. And what was most impressive, I think, was that not only that this thing was walking around, untethered, and you're going to see it's walking upstairs. I mean, this is impressive stuff. This is, maybe not so different from what we had to do in the DARPA challenge recently. I mean, just super impressive things to do with a really complicated robot, fastening a bolt, right? This is in 1997. Walking upstairs. This sort of shocked the world of robotics, right? That we could have a humanoid robot that looked this incredible. Okay, but there's still something sort of annoying about the way that robot's walking around, right? So it's walking around with its knees bent. It's walking around. It doesn't look quite natural. It looks kind of like a guy who's in a spacesuit who isn't quite sort of able to move the way he wants to move, right? And in fact, there's a huge penalty for walking that way, right? So you can imagine if you walked around like this, then you'd get tired fairly fast. Okay, but also Asimo is doing more than that. It's actually using very high gain feedback to effectively cancel out the dynamics of its legs when it's walking around. Okay, so in some way you could say that Asimo is sort of walking like a robotic arm that you might use on an assembly room floor, and really not walking like a human. Okay, there's another approach. This is a robot, well, it doesn't have any motors, any controllers, any actuators whatsoever, okay? It's really a toy, a big glorified slinky. You put it at the top of a ramp, you give it a little push, and you let gravity do its thing, and guess what? It looks, by most accounts, better than Asimo when it walks, right? It's not as versatile. It has to walk down a ramp, that's all it can do. It can't turn, it can't do anything else. But it's pretty compelling demonstration that actually, this high gain, stiff walking of Asimo isn't necessary, right? It's also clear that it's not necessarily good to be walking with high gain, stiff, cancel your dynamics. The energetics of Asimo are impressive. I mean, it takes about 20 times as much energy as a human when we walk, right? It's scaled for the mass of the robot. Okay, so there's another approach, and this is sort of from the side. It just looks beautiful. It looks like a guy walking through the park. All right. The video I would love to show you, but we don't have yet, the field doesn't have yet, is a robot that can walk like that, walking around, going upstairs, and doing all the other things. We don't have that as a field yet, okay? But there's something really deep here about letting physics do the work, and that's a really, really hard thing to do. That's sort of it's a change in the way we have to think about control. Okay, so it's really, really hard to sort of let go of control and let the world do the work for you, because that means you're not in control. And if there's uncertainty in the world when you're moving through unknown environments and things like that, that means you're giving up control to something you don't completely understand. It's a hard, scary proposition, and control theorists, I think, have been reluctant to do it so far. Okay, but we're getting to this great place in robotics. Let me see if that'll play better. Wow. Try that one more time. The slides are in HTML5 too. Maybe it's a... It's that screen grab going in the background. How many people have seen Wildcat already? Yeah? All right, it's pretty awesome. Okay, so we're at this place where we can build some of these incredible machines moving incredibly fast, but it would still be extremely hard to have Wildcat doing that in sort of unknown environments. And I think even though we can make YouTube videos of this, this kind of performance, I think the solutions we're fielding as a field in robotics right now are still extremely frail. They're sort of surprisingly fragile. I think Boston Dynamics is a leader in robustifying that, but right, they're robustifying it by putting tons of man hours in. And I like to talk in this course a lot about how to make robots dynamic like that and have robustness be a common theme, where we're going to really try to make robots perform tasks robustly. Awesome. Yeah, there you go. Okay, so and then recently, Tuan and Robin and I and an awesome team from MIT took a robot like this. It's Atlas, built by Boston Dynamics, and we had it drive a car, open a door, turn valves, pick up drills, cut through walls, walk across rough terrain, climb stairs. It was an awesome, awesome, awesome project, exhausting in every possible way, but hugely impactful on my view of the world, and just a ton of fun to do. And we'll certainly talk about that kind of stuff in class today. But so we're able to field robots today that can move around. You see that Atlas is actually moving not so different from Asimo, right? So it's hugely inefficient, and it's sort of surprisingly frail. I couldn't bring it myself to show you the falling down video that you've probably seen on YouTube of this every robot falling down and crashing and breaking its head open and things like this. I didn't have it in my heart to show that video, but I think the DARPA challenge revealed not only how capable these robots are getting, but also that there's still some fragility in the system. Okay, so if you don't care at all about walking robots, I think there's still something for you here. It turns out the story is almost exactly the same if you think about aircraft. Okay, so on the left here we have a F-14 doing a runway landing on an aircraft carrier. Okay, so fighter jets are some of the most sophisticated automation that people have fielded. Some of the most advanced control systems. The field of robust control grew up partly in response to the need for fighter jet control. Hugely advanced system, right? But still, when a fighter jet lands on a runway, it's coming in at a very shallow angle relative to the runway. Okay? If you look at a bird, when he lands on a perch, he comes in at a completely different angle of attack. He comes in with his wings flared. And what's the difference is that when you flare your wings and put them out like a parachute, you can stop much more quickly. So a bird can land on a perch, and the aircraft takes the entire runway and has this hook hanging down because you have to actually have to grab the guard wire. If you miss the guard wire, you got to hit the throttle and take off again. Otherwise, you plunk into the ocean, right? So the reason that we do this in the control is because when your aircraft is at a low angle of attack relative to the flow, then we have good piecewise linear models of the aerodynamics. Okay, so this is a wing with these lines being the streamlines. And when the aircraft is sort of in line with the direction it's moving, then the air moves nicely around the wing. If I bring my angle up to a small angle of attack, again, it stays connected to the wing. And then if you, somehow the images didn't actually update, that's too bad. This one's supposed to be a stalled angle of attack, okay? If you raise your wing to too much of an angle of attack, the air basically can't bend around the wing. It will separate, you'll get a vortex shedding phenomenon. And what happens in the modeling, if you care about designing a control system, the system becomes very nonlinear, okay? And effectively, we haven't had good tools to control those systems. So that's why these aircraft are coming in at these, I mean, even this most advanced, so much research money invested in this, and they're still coming in at very conservative angles of attack. So very much like Asimo, the reason Asimo walks like this, not relinquishing control to the dynamics, is because it wants to stay in a place where it's in complete control. It's willing to expend extra energy to sort of be in complete control so that it can act effectively like a robotic arm, okay? The aircraft are doing the same thing. It's staying in a very conservative envelope of operation because that's where our control theory works. And if we go up and let the dynamics take control, we don't actually know how to do it. Birds do it all the time, right? So this is one of my favorite videos of a Eurasian owl coming in for a landing basically on the camera. Look at his wings. Look at the leading edge of his wings, right? So the feathers flipping up, yeah, are indicative of stall. Yeah, that's how you get a good video, is you put something in your hand in front of the camera, right? And these guys are just doing beautiful, beautiful perching maneuvers. So one of the other things we've done in our lab, and the kind of thing I want to talk about in this class, is how do you make an airplane do something like that, right? So it turns out if you're willing to solve the dynamic problem and the nonlinear control problem, then you can make an airplane land on a perch like a bird. There's nothing mechanically stopping an airplane from landing on a perch. It's really a control problem. So that's a high-speed video slowed down about 11 times, and that's the plane just a foam plane getting launched out of a launcher, going up, stalling its wings and landing on a perch. Okay, so just to convince you that it's actually in a complicated nonlinear regime, we put smoke on the leading edge and took pictures of the vortex shedding, and it's indeed going through these really complicated maneuvers. Okay, now we've been working a lot on trying to make this robust. So Joe's final thesis was showing that he could land on the perch every time from hand-thrown initial conditions. So I think the tools from the class will get you somewhere along this road, but it's still an active area of research. And I'll try to walk that line for you and tell you what works, what doesn't work, and where you should contribute. Okay, so animals, there's tons and tons. I have a hard drive full of videos of animals doing impressive dynamic things. Let me just tell you a couple of the stories because they're just fun, right? So some of the metrics that you see from animals just thumping our best engineered solutions, right? So if you look at the cost of transport of an albatross flying across the ocean, okay, it's actually, the cost of transport is actually about the same as a 747 going across the ocean, which the scale is pretty impressive. But what's really impressive is that if you look at the metabolic rate of the albatross as he's flying across the ocean, it's indistinguishable from what he's doing when he's sitting on the beach, right? So he could be just really inefficient on the beach, which is probably true. But it's still pretty impressive that he's flying across the ocean, powered almost completely by a phenomenon of dynamic soaring, where he's using the gradient in the shear layer over the ocean to effectively use the air to push him through, even if he's going upwind or downwind, you name it. Okay, so these guys are incredibly efficient. If you look at maneuverability, aspects of maneuverability, animals are thumping our best engineered solutions too. So, peregrine falcons are known for diving at up, some people say 180, some people say 250 miles an hour, incredible speeds. That's not actually that impressive to me. I mean, a bullet moves pretty fast, okay? What's impressive is the video where he's diving 250 miles an hour, and then he pulls out of that dive to catch a sparrow, right? He basically, in mid-dive, will do some evasive maneuver, turn in a few body lengths, and grab some other fast-moving object, right? That's what we can't do with a bullet. I guess that's not my goal in life, but it's impressive, right? This is a great video from Berkeley of a hummingbird eating out of a feeder in a wind tunnel where the air's blowing, okay? He just looks like he's sitting there. But what's impressive, you see the arrows on the airflow, right? So he just looks like he's just having a good old time. The wind's blowing at some incredible rate, 10 meters a second or something like this, okay, for a little bird. But what's really impressive is that he's actually flying backwards at about 10 meters per second while he's just sitting there, lazily putting his beak in the feeder and doing his thing, right? There was actually a great New York Times piece about the way they use their tongues to get the food out just this week. Okay, and then this is my favorite video of all time, okay, to sort of convince that biology is using dynamics, even if our engineered solutions aren't, okay? It's from George Lauder at Harvard and Mike Tranafilou, who's in our department here, mechanical engineering department here, okay? So this is a rainbow trout. This is my one video that didn't work well with HTML5 here. Okay, so this is a rainbow trout viewed from above in a water tunnel, okay? So the rainbow trout are the fish you hear about that swim upstream at mating season, and it's sort of incredibly impressive how much, how much work it seems that this whole flock of fish will do trying to swim upstream, okay? So they took one of these fish out and put it in a water tunnel, and that's what it looks like from above, okay? This is the same rainbow trout now when it's put behind a rock. So one of the things they notice when they're watching these fish in wildlife is they seem like they'll take a break and hang out behind a rock every once in a while. Okay, so what they did is they put a cylinder upstream in the water tunnel. If you put a cylinder in a water tunnel, you'll get a vortex shedding phenomenon. And you put the same fish, look at it from above, and if you see what it's doing, it's swimming in a pretty different way. Sorry, it's annoying about these videos here, okay? Swimming in a pretty different way. They called this the von Karman street, okay? So the von Karman gate, right? So this fish seems to be somehow doing something very clever, sort of swimming between the vortices or something like that. And the claim was maybe it's doing something energetically intelligent, okay? But the clincher for me is this last video, okay? So this is another fish viewed from above. You can see the obstacle here this time. This one's a dead fish, okay? There's a piece of string keeping it so that it doesn't go back and get caught in the grates. Talked to the guys that did this, they said, yeah, that would have been just an experimental nightmare. So they've got a string, a piece of twine, sort of making sure it doesn't go back too far, okay? The fish is getting knocked around by the vortex shedding of the half cylinder here, okay? So that's not too surprising, right? Fish is flopping around. Okay, what's pretty cool is when you realize the water's going this way, okay? And the fish just went that way, and the fish is dead. So it shouldn't be able to do that, right? So there's something very, very, very clever going on where it's clearly not the control system in that case. It's somehow the mechanical system is designed and optimized in such a way that it actually passively resonates with the dynamics, turns circulation this way into forward propulsion that way, right? Just a beautiful, fun example of sort of dynamics being exploited in nature. So my claim is that we should be doing this with all of our robots, and we're really not yet. Okay? So again, I think this is relevant even if you don't care about walking robots or dead fish. Let's say you're a perception person, okay, and you just want to think about how to make computers see the world better, which is a hugely important and difficult topic. Okay, so this is just a clip from Lawson Wong, who's up in Leslie and Tomas's group upstairs. One of the things he likes to talk about is the fact that the most estimators that just use, let's say, a Kinect or a laser scanner in the head and look at point clouds off an object and try to estimate where the object is, they have this annoying property that they'll give you some probability that the object is, let's say, in penetration with the table, right? It's stuck through the table, or multiple objects. That the most of the estimators we come up with right now have things that are in collision, right? And his work here was trying to take them out of collision, okay? But they also have this problem that they'll often predict that the cup is like floating in the air, or it's like this, or it's like this, okay? If you just put a little bit, there's obvious priors coming from static mechanics that says that there's basically, if the system's there and it's not moving, then it can't be in this configuration. It can't be in this configuration, right? So I think that one of the things we're working on in the group, and I think one of the things that you're going to see as a theme in perception, I hope, in the next few years, is that with a little bit of reasoning about dynamics, our perception systems will get much more intelligent about the world, okay? And that's true in almost every area of robotics, I think. There's a role for dynamics to play. If you care about quadrotors, we'll show you how to make quadrotors that can dart through forests. And this is a synthetic simulated forest, but we'll actually show you the videos of the real planes and quadrotors flying through forests too. And we have quadrupeds walking around and all these things, okay? So if you care about vehicles, boats, cars, airplanes, legs, you name it, I think there's going to be a role for dynamics in the work you're thinking about. Actually, I would go so far as to say if you look at what works and what doesn't work in robotics today, I think almost all the areas that don't work well have some role, have some problem because of dynamics, right? So certainly in the control space. I mean, the other place that you'd think about that's a really hard control problem maybe is manipulation, okay? So manipulation is hard because of the dynamics too. So even if I have an arm that I can control very easily, right? And we'll talk about whether it's underactuated or not. Somehow manipulating an object suddenly becomes a problem that has dynamics you can't avoid reasoning about. Okay, so let me stop skirting around the definition of underactuated and dive in and start defining a few things, okay? I should also say that the problem of thinking about dynamics in robotics has sort of everything that you'd want in a research topic, right? You get to work on fun robots. You get to solve. There's fundamental mathematical puzzles that need to be solved. There's serious software problems that need to be solved. There's pretty much anything you want in a research project. You'll find it if you care about dynamics. Okay, so I'm going to try to not assume a robotics background in the course. I can't help but assume, we assume that you come in with some comfort in linear algebra and in differential equations, but I'm not going to assume that you know, for instance, all your robot kinematics and dynamics equations, because really, I can show you in the notes in a few pages and get you up to speed on that, and that's not a huge prerequisite, okay? But one of the things you're going to see a lot in the class is sort of vector differential equations, okay? So let's start doing definitions. So one of the things we're going to care a lot about are these nonlinear differential equations. Okay, and in fact, what we really care about is control differential equations. Okay, by that I mean a pretty general form. We're going to write equations down that look like this a lot, okay, where x is our state vector of the system. I'll give you some specific examples in a minute. Okay. U is our control input. F is a vector valued function. Real. We're going to stick to the real numbers. And x dot is the time derivative of the state. Okay? We'll occasionally have time-varying dynamics and other things, but this is the canonical form of a nonlinear control differential equation. So U is the thing that my actuators are going to do. It's the output of my control system potentially. It's the thing I get to choose in this equation. So I get to pick what U is. I get to design U in order to try to make maybe X do something that I want. Okay. Now, essentially every system that we care about in class is going to be a mechanical system. And those have extra structure. Okay? For mechanical systems, we know F equals ma. You know, that implies to me that these things are second order systems, okay? At least. So we're going to use a little bit more refined notation, I guess. If we're going to say Q is a vector of positions or configurations of my robot. So that could be a list of all the joint angles, for instance, of a humanoid robot. Okay. We'll write Q dot as the velocities. Okay. In the code that we'll give you, you'll often see this written as v. It's a vector v instead of q dot. That's for an important reason. If you start writing down the dynamics of rotations in 3 dimensions, then the dimension of q and the velocity vector need not be the same size. It's often not the same size as the position vector, so it gets a new name, v. But for the purposes of the course, we're going to get away with q dot, and that keeps all the notation simpler. Okay, but you can v for q dot is an easy substitution if you need to in your head see that in the code. It's no big deal. Okay. And so now our dynamics of relevance here is a second order dynamics. We're going to describe how q double dot changes, what the accelerations are as some function of q dot, and u. Okay? And these are all, I'm using this shorthand, right? I really mean that I could be writing this out explicitly with time. Okay, in fact, the systems we care about have even more structure than that. It's not just that they're second order. Almost every system we care about in this class and in life has an additional property that it's control affine. Okay? So that means u enters the equation in a very particular way. So the dynamics are affine in u. Okay, so you'll be able to write the system in a more specific form. Like this. Just being extremely explicit about how u enters the equation. And we're going to take advantage of that all over the place, okay? And that's really just saying F equals ma again. So if my control inputs are torques from a motor or forces from some motor, then my accelerations are affine in those forces, right? So I might have some contributions from gravity, okay, but apart from that, if I put in more force, I get more acceleration, right? In a linear way. Okay, this is enough structure. So one of the themes from the class that you're going to see over and over and over again is that we're going to take our dynamical systems, we're going to take this, written as some differential equation in F, and we're going to pull apart F and try to find the structure in F, right? So the dynamics that govern my body as I move through space have all kind of structure in it, right? So there's a, when I wiggle my left pinky, it really doesn't have that much of an effect on my right hand, right? There's some sparsity in the equations, okay? There's structure like this, the way that the control effort goes. One of the themes we're going to do again and again and again is we're going to try to break apart F, exploit the structure that physics gives us to be able to make algorithms that can reason about that efficiently. All right, so this is enough structure for me to at least define underactuated in a very, I think, very intuitive way. Okay, so we're going to say that a system given in this form call this equation 1 is fully actuated. Let me define fully actuated first. Let me write it down and then we'll make sure it makes sense. Okay, so let's think about that. So the role that F2 plays in this function, this is a vector valued function, so F2 is a matrix valued function of its inputs, Q and Q dot, right? So for any particular Q and Q dot, F2 is a matrix, right? The matrix, that matrix will have some rank. Let's think about the size of that matrix. So let's say that the dimension of Q is n, right? So it's just a funny way of writing Q lives in Rn, okay? And let's say the dimension of U is m, or Q lives in Rm, okay? Then what's the size of F2, the matrix for some particular Q and Q dot? What's the size of F2? Q double dot's going to live in Rn also, right? So this is going to be this is a vector. When I'm talking about vectors, I'm always going to talk about column vectors in the course, unless I say something otherwise. So this is going to be m by 1, right? The output over here has got to be n by 1. So this thing's going to be, that means F2 somehow lives in, it's an n by m matrix, right? So we'd like F2 to have rank n, ideally, the same dimension as Q. Okay. What does that mean? That means I'm going to be able to take an inverse of F2. And why is that important? Basically, if if I can take an inverse of F2, then my claim is if your robot has a dynamics of the form where you could take an inverse of F2, then your robot is simple to control. If you can't take an inverse of F2, it's really hard to control, or it's harder. That's what we're going to talk about here, right? So, of underactuated system. means I can't take F2 inverse, okay? One thing I want to note is that to be careful, I want to allow for the possibility of this being a property, whether the system is fully actuated or underactuated depends on what configurations it's in, right? So it's actually a configuration, state dependent, it's dependent on position and velocity in this case, property of the system. We'll say that the system is underactuated if this is ever the case, right? If there's any Q and Q dot for which this is true, we'll call it an underactuated system. But let me make sure you understand why this is such a big deal, okay? And why all of the interesting robots in the world have this problem, okay? So, the big deal is that there's sort of two types of systems in the world when you're thinking about control. There's the linear systems. If I have a system where I can write down the dynamics like this, then we have a huge repertoire of powerful control tools to reason about that system. If A and B are unknown, we have tools for that. We just know a lot about how to solve that set of equations and design U for that. Okay, we can design optimal controllers in many cases. There's things we don't know still. It's fair, but we know a lot about how to control a system like that. Okay, and then there's sort of the nonlinear, which is always a funny name, like the non-elephants, right? But the nonlinear systems, which unfortunately includes the linear systems, right? But if I have to stick to this more general form, then there's much, much, much less that's known, okay? Now, the nonlinearities in these equations, the things that make it so you can't write it down like this, in most cases, that's the good stuff, right? That's the stuff that we're going to be able to exploit. That's the fish pulling energy out of the vortex. That's the dynamics of my robot swinging its leg through, right? That's the good stuff. We don't want to get rid of it, okay? But we gotta think about it. We're going to have to reason about those nonlinear dynamics. All right, so here's the trick. If I'm given a robot, which all my robots, because they have, almost all my robots in the world have some nonlinear terms f, but if they're fully actuated, then I claim that they're easy to control, and maybe you can see why, right? So if I'm given my Q double dot, my second order system form, let's say I'm going to write down, remember I get to choose U, that's the name of the game. I get to write down a controller that gets to choose U, okay? So let me write down this particular controller. Okay, let's say I have some desired acceleration of the system, right? I'd like it instantaneously to go in some direction, okay? Then I'm going to put that into through a map. I've also assumed here, that assumes that F1 and F2 are known. So I have a good model of my robot, okay? Everybody see my dots and everything okay? Just squawk if something's hard to read. And I put a D in the superscript here. So what happens if I take this control law and enter it into these dynamics? Well, since F2 is invertible, that term goes away. This will cancel this term. And what I end up with is that the dynamics of my robot, the actual accelerations of my robot, are going to be the desired accelerations of my robot. You could think of this as a different system, q double dot equals u, right? Whatever I want to choose. It's basically I've converted my system from a nonlinear system into a linear system. Not any linear system, the trivial decoupled linear system, right?
Do you, when you go from the first line to the second line,
yep.
would you add some parentheses around the last portion of the term to the F2 inverted?
Oh, did I? Okay, yep. So, absolutely, yeah, I should go like this, right? Okay. Thanks. Thanks. Good catch. Okay, so this is a simple trick, right? It's known as feedback linearization. I can give a feedback control law that turns my nonlinear system into a linear system. Not just any linear system, this is the trivial linear system. Okay. Another way that people might say this is that the system is feedback equivalent to q double dot equals u. Right? Through a simple feedback law, I can change my dynamics into a dynamics like this, and I know everything about how to control that system. Right? We can make it do whatever we want. It still can't follow arbitrary trajectories, right? It's still a second order system. But we know a lot about how to design that to do what we want. Okay? So, long story short, if you have a well, let me wait and tell that story with the manipulator equations. Okay, so there are other things that can break this, taking this inverse, that can break feedback linearization. Okay, so having F2 lack rank is one of the simple ways to do that. If its F2 is not full rank, and we'll show you examples of that, how that plays out. You can also break the ability to do feedback linearization by having constraints in the system, other types of constraints in the system. Right, so if you're a little robot and you've got little motors, right, and for instance, maybe you have input limits. Like my torques have to be less than 1 or something like that. That can also break this trick. Even if F2 inverse exists, it might be that I can't apply enough torque to turn the system into this, right? Into that linear system. State constraints can get in the way too. State constraints show up all the time, like if I say that my object is moving through space but can't penetrate the table. Or I don't want my quadrotor to fly into the tree. Other things that can interfere with the ability to just change the dynamics arbitrarily. Okay, so there are other ways that you can break this ability to do feedback linearization. And so the generalized definition for underactuated is really what I care about is some system of even arbitrary order, but I'll just write the second order system. It could have time dependence. It's got a control input u. What I care about is the properties of this map F right? So, sorry to run out of board there. It's underactuated if basically I want, for every q double dot, I need that there exists a u which generates that q double dot, right? I'd like to be able to produce arbitrary accelerations, right? I'd like that map to be well defined so that I could, for every q double dot, I could pick a u. If I want to accelerate in some direction, I can do that. I can find the u, right? And input constraints will break that, and other constraints will break that. And that's written carefully in the notes, okay? Yeah, please.
Is that for underactuated, or?
So I would say that, so in a particular q dot and t, the system is underactuated if you can't produce arbitrary accelerations, and the system is underactuated if this ever exists.
Okay.
Yeah? Oh, you're saying I wrote this back. It's
Yeah, exactly that.
Yeah, exactly backwards. Thank you. That's important. Thank you for catching that. Okay, so let's talk a little bit more about robots in particular and how to recognize underactuatedness in a robot. Okay. So let's take one of the simplest examples of a simple double pendulum. Okay. So here's my simple robot. I can describe its configuration with two variables, theta 1 and theta 2. Okay, I'll give it mass, 2 point masses, m1 and m2. I'll have gravity pointing down here. Okay. You don't have to be able to write the equations for this system to get through this class, but I want you to know it's not hard. It's a good life skill, right? It's very easy, and there's also very good algorithms that'll do it for you these days. Okay, let me just sort of show you the sketch what you would do, right? So one of the ways to do it is with the Lagrangian mechanics. Okay, so I can write down the energy of the system very easily if I just write down where the mass is as a function of my coordinates, right? So I can write down, let's say, the kinetic energy. Well, let me start by even just writing the kinematics. I won't do this at length. It's all in the notes just to give you a sense, but I just want you to not be afraid of it. It's pretty easy. Okay, so if this has length L1, length L2, then the position in space of my first mass is just, what, L1 sine theta 1, and then negative L1 cos theta 1. And I can easily write P2 also. It's just that position plus L2 sine of theta 1 plus theta 2. You don't have to write this down. This is just to make sure I'm not pulling a rabbit out of a hat when we talk about dynamics, okay? I could take the derivatives of that. I can write down what P1 dot is by just writing that down. I get a L1 theta 1 dot cosine theta 1, right? This is standard stuff, and again, this worked out carefully in the notes. I can write down what P2 dot is. I can write down the kinetic energy of the system. We'll call it T. It's just 1/2 mv squared. Since I've got point masses, it's just that simple. Just to make the transition in a minute, I could have also written this as P1 dot. This is a scalar. You know, I could have written this as, I should have written it. In fact, it's a vector. No? I should have written this as a vector notation, since I've written that this up here is a vector. Okay, I can write the potential energy, you name it. I mean, it's very simple, right? I basically get mg, then the y coordinate of this, m1g1 y1 plus m2g y2, let's say. I can use Lagrangian dynamics. You can really just turn the crank. It's a beautiful variational principle, but you can just turn the crank and write down the Lagrangian, take some derivatives, and spit out some equations, which, to save myself some writing and to save you the boredom of watching me write it, come out with something like this, okay? So if I write those equations down, take the derivatives, I get one equation for each equation of the form like this. There's standard ways to write those equations. And for the simple double pendulum I wrote here, those are the equations you get, okay? So this is almost exactly in the form we've been using, this q double dot equals something, okay, on the right-hand side. If you look, there's a couple things you should notice about that. The torque is the input. The tau is my little u, my control input, tau 1 and tau 2, okay? And you see the q double dots, q double dot 1, q double dot 2. If you write this down enough times for enough robots, okay, you start to see some patterns emerge in those equations. And there's even more structure in the equations. It's not just control affine. They all subscribe to the famous manipulator equations, okay? So it turns out I can write, if I go through this process for my robot, whether it's the cheetah robot or a double pendulum, I'll come out with something that takes this special form. Sorry that the board's kind of marked up, so you got to make sure you can see all those dots, okay? This is basically another way to write down my little f, okay? But it's even got more important structure, okay? So this thing is called the inertial matrix. It has properties. It has properties that we're going to exploit a lot. So it turns out it's clearly related to the energy. I could have written sort of a generalization of the mass. It's the mass matrix, okay? I could have written it as q dot h q dot. It's just like that mass, the role the mass plays in that equation. Now in the vector matrix generalized version of it, okay? It depends only on q. It doesn't depend on q dot. That's important structure. And maybe by virtue of saying it's an energy, you can sort of believe that it has this important property that it's always greater than 0, okay? When I write a matrix greater than 0, I mean that it's a positive definite matrix. I'll be careful, I guess you could have a 0 mass system, but it also happens to be symmetric, okay? For any reasonable system, it's strictly positive definite, so we'll, because I'm going to invert it in a second, so I better make it strictly positive. Okay? And it's just gobs of structure, okay, in these equations. This is the Coriolis terms, roughly speaking. It has structure, you know, there's H minus 2c is skew symmetric. There's all kinds of structure like this. This is roughly the potential, this is the gravity terms, that's why it's got a G. Terms from potential energy. You know, these Coriolis terms always have a component in Q dot, and it's control affine. Right? The fact that this H is invertible means I can go through and take this. The fact that it's positive, it's a positive definite matrix, it means I can always take its inverse, so I can write it back in the form that's more familiar to us. This with a big complicated F. I got my signs wrong. Something like that, right? Right, I can write this as, again, my nonlinear differential equation with just Q double dot on this side. And F1 is sort of all this stuff. F2 is H inverse B, right? Everybody square on that, yeah? Okay, so let's say you have a robot, and you've called your software, you've done your derivation, and you've got this equation. What's going to tell me if it's underactuated or not? What's the easiest check? If B is square, but and B actually has to be full rank, right? It could be square, but have zeros in it or something, right? So if B is invertible, so since H is always invertible, it turns out that the requirement for F2 to have full row rank is that B be full row rank, okay? It's fully actuated if B is full row rank, okay? B is this term that maps my torques to my joint space. Okay, this is maybe my gearboxes or something like this. This is my map from torques to joint coordinates. If B is full row rank, then I've got a fully actuated system. It's easy to control. If B lacks rank, then I've got a harder problem. Potentially a good problem, but a harder problem. Okay, so in my simple double pendulum example, if I have if I have a torque motor here and a torque motor here, tau 1 and tau 2, if I were to write that in this manipulator form, then B is going to be the identity matrix, the 2 by 2 identity matrix. That system has full row rank. It's fully actuated, right? I can do whatever I want to that system, and we will in just a second, okay? If for some reason we were to leave an actuator off, let's say we've got an actuator in the elbow but not in a shoulder, okay? Then suddenly B drops rank, and I've got an underactuated system. So Manoli, who was actually who's teaching in the class just now, he likes to tease me. He says, Russ, if you had more funding, would you work on fully actuated systems, right? It's not just if you can't afford more actuators. There's actually fundamental. So that seems like a weird thing to do. Like, okay, we forgot to put a motor at the shoulder. All right, that's not the point. The point actually, even though it seems silly, is that model, as drawn with an actuator at the elbow but not at the shoulder, is actually effectively the model we're going to use to understand walking. Right? That is one of the simplest models of walking robots. Okay, why? Why do I need that? Basically, I'm a big complicated system. I've got lots of actuators. I probably even have, depending on how you count them, I maybe even have more actuators than I have joints, right? Because I've got multiple muscles that span multiple joints and things like this, okay? So if you just count, I might actually have more actuators than degrees of freedom. But it depends on what level you model, okay? But somehow, when I jump, right, those muscles do me, let's neglect aerodynamics for a second. When I'm flying through the air, nothing I do with my muscles is going to change the trajectory of my center of mass, right? My system is underactuated. And it's because I'm not bolted to the ground, right? I've got this beautiful, complicated robot, and that last joint, the one that connects me to the ground, I don't have an actuator, right, at my foot. That's just like not having an actuator at your shoulder here, okay? And so a walking robot is underactuated, okay? Airplanes, quadrotors, they're not attached to the ground. Quadrotors, if you have enough, if you have enough actuators, then you get some of the properties of having almost a fully actuated system back. We'll talk about that, okay? But a lot of interesting robots are underactuated. All interesting robots, let's say, are underactuated, right? So if I'm a manipulator, let's say I'm bolted to the ground, okay? And I've got complete control. I can command any arbitrary accelerations. I got huge motors. I can command arbitrary accelerations of my arm. But now my task is to pick that object up. That object has 6 degrees of freedom on its own, right? And I can't control them directly. I mean, there's a particular case where if I get myself into some comfortable grasp and I somehow fuse, if I consider the object's degrees of freedom fused with my own, then maybe there's no degrees of freedom and I can do arbitrary things to that object. But in general, certainly getting into the grasp and things like that, I have an underactuated system. That's why manipulation is hard, I think. Uncertainty is the other good reason. Yeah?
So you mentioned needing an actuator to fully control this at the other joint.
Yep.
But could you control it by moving first actuator in another? So
that is the topic of the course. So having not enough actuators means you can't instantaneously accelerate in arbitrary directions. It doesn't mean that you're necessarily very impoverished as a control system. It just means that you have to be more clever. I can't make this system look like an arbitrary linear system and apply linear control techniques. I have to think about F, okay? I have to do more sophisticated control. Okay, so let's do it just as a sort of an example to show you that this system is trivial. If I have both actuators, it really is trivial to control, right? So I can take that robot and make it do whatever I want. Okay, so one of the things you might want, let's say I've got a double pendulum. By the way, all these equations are going to be, hopefully very accessible to you. So if you, they're all those systems we care about are typed in. You're going to be able to download this MATLAB code, and you'll be able to see. I've typed in the H, C, and G matrices for this particular simple double pendulum, and you'll be able to run everything. Let's see, the very first time you run it, it's slow because it loads Simulink, or maybe just because I have my figure in the background. Okay, so this is just a passive double pendulum. If I have no control input, it just swings like a double pendulum. Okay, but let's say I wanted to do more. Let's say I wanted to make this double pendulum, I'm going to replace its dynamics, right? I can do anything I want to this. Let's make it act like a single pendulum, okay? So what would that be? Let's say I wanted, I've got like the smallest chalk in the world. There's got to be a better chalk. There we go. A whole bucket of better chunks. Okay. Let's say my goal in life is to make this act like a single pendulum. So maybe I want this to look like negative g over L cos theta 1. I'll give it some damping, okay? So maybe I want the first degree of freedom to just act like the equations of a simple pendulum, and I'd like the second one to do nothing. Okay, that's not really good. I should stabilize the second one really, but let's just keep it simple for now, okay? Then I could write a controller that just imposes this totally different robot's dynamics on top of my dynamics, right? So I could just write down my feedback linearizing controller, which is exactly what I did before. I'm just going to take F2 inverse. The way it plays out is it looks like this. Okay, if I write down some controller like that, type that into MATLAB, which I've done, and I simulate that forward. This is the feedback linearizing controller. It's going to make the resulting dynamics, Q double dot equal this, theta 1 double dot desired, theta 2 double dot desired. Okay, and I can simulate that. Okay, and assuming I started with theta double dot equals 0, since I didn't stabilize it here, then it's going to act like I've just replaced the dynamics. I've taken my beautiful second order 2 degree of freedom dynamical robot, turned it into effectively a 1 with just using high gain feedback, right? Those motors are potentially doing a lot of work to make that happen, but the math is easy, right? In fact, I could do the same thing if I just flip the sign of gravity, right? Then I could even make it look like an upside down pendulum, right? Right? If I want to balance it at the top, well, just make it act like an upside down pendulum. That's no problem, right? That's easy. The math is easy, right? If I have torque limits, I can't do that, okay? But the math is easy, right? So feedback linearization is actually a beautiful, powerful thing to do, right? You should do that when you can. Maybe you should feel bad about it if you do that, but it's a powerful tool to have in your toolbox. It's one of the things that powers, for instance, some of the strongest adaptive control results we have in the field. It's a hugely powerful observation, the fact that you can do this, and there's extensions of it in adaptive control. For instance, if F1 and F2 are not known perfectly, but they're estimated, you can still do some powerful things. It's great, okay? But most systems that I care about, you can't do that, right? You can't invert F2, so you got to do something extra. Okay, so just since I've got the software open, we're going to give you this software package to download. It's got all the dynamics and tools that you should need for the class. It's in MATLAB. If you care about C, you can help us. We're porting it all to C++, with Python bindings and all that. But you should probably use the MATLAB version. It's more mature. Okay, and it's kind of fun. The same thing you download. You'll just have a package to download, and you'll sort of instantly have simulations and you'll see all the control we do on Atlas and all that stuff is all right there. It's not fast on my laptop, but it'll start walking around. Okay, so I hope you play around with it. I hope you don't feel like it's a black box. So the first time we gave this away, it's actually really a lot of work to give this away, by the way. So we spent a lot of time on it. Okay, he's not moving yet, huh? Oh, it's because I shut off the network and back on, so it's not talking. He got confused because of the Wi-Fi, sorry. Here he goes. The C version's faster. But yeah, so the software is there for you. One of the great things about being in MATLAB, there's precompiled versions if you want, but the MATLAB code, it's interpreted code. You can open up the file, you can look at it. There are no black boxes here. If you want to know how something works, first appreciate that we'll be able to work at a level of abstraction where you don't have to derive the equations of motion for something like Atlas. That would take a lot of paperwork. Okay, but also if you do care about how we do it, then open up the code and look at it and go figure it out. Right, it's all there. Okay, so here's the plan for the course. That gives you some of the basic definitions. Right, this is really a course about dynamics and how you make your robots think about their dynamics so that they can be awesome. They're going to move faster. They're going to reason about the world better. They'll be more robust, hopefully. And the approach we're going to take is actually a very computational one. Although we didn't do that yet today. The reason I care a lot about the structure, the particular structure that I care about in the equations, are the structures that we can take advantage of with computer algorithms, right? So with algorithms implemented in MATLAB, for instance, right? We're going to write a lot of algorithms to try to design controllers to make Atlas walk. We're going to design controllers to make airplanes land on a perch. We're going to try to tell you everything I know about that kind of that set of tools. And really, the class will hopefully leave you with a pretty powerful toolbox for applying these tools to your own systems. They're all pretty general. In many cases, we'll give you specific examples of specific controllers on specific robots, but you'll be able to immediately apply them to a different robot. So that's roughly the way I want to organize the course, right? So we're going to start simple, okay? I want to start actually even simpler than I did today. The next lecture will be a simple pendulum, okay? We're going to talk about the basic concepts from dynamics, right? So I want to make sure you understand the phase portrait. I want to make sure you understand what bifurcations are, what stability means, some basic concepts from dynamics. For those of you with a dynamics background, that'll be slow, but maybe I hope that I'll show you some views of that are a little bit different than what you've seen before. And it's meant to put us all on the same page. We're going to quickly go to some of what are the classical underactuated systems. So there's a few that you might use in any textbook, like a simple pendulum on a cart, called the cart pole system. The double pendulum I talked about that has only an elbow actuator here this is called an acrobat. Cart pole. We'll do quad rotors then too. Okay, these are sort of maybe the canonical underactuated systems that are missing actuators because someone left them off. Systems, okay. For every time we introduce another robot, it'll motivate a few more algorithms. And I don't want to give you algorithms without giving you a robot that needs that algorithm. So it turns out that we're going to be able to do everything we want to do with the pendulum just using dynamic programming. And that'll be a nice way to sort of introduce the ideas of writing control problems as optimization problems, okay, using the language of dynamic programming. But dynamic programming is already going to start breaking down when we want to control the canonical underactuated systems. So we're going to extend our toolbox to do stabilization, trajectory planning. In particular, we'll do trajectory optimization at that level. We'll do talk about partial feedback linearization. And we'll even talk about stability verification, nonlinear stability verification using something called sums of squares optimization. Okay. And then the systems get more complex in a couple different ways, okay? So we'll actually, because I love walking robots, we'll spend some time working on understanding the details of walking robots using both simple models and complicated humanoids, okay? And that's going to introduce us to some of the concepts in, new challenges that come from having a system that's not only underactuated, but it has impacts with the world. So you end up with hybrid dynamical systems. And we'll try to extend some of these tools into the hybrid systems. We also, walking gets us to talk about periodic behavior, limit cycles. Okay, and we'll talk about humanoids, some of the special tricks you might play if your system's as complicated as something like Atlas. Okay, we're going to talk about more high-dimensional systems. Instead of drawing a silly robot, I'll just write high degree of freedom. Okay, and complicated geometry. Talk about motion planning in this case, using more advanced tools or more different tools from motion planning, sometimes randomized, but also mixed integer type planning and other things that you might have heard about to handle more complex situations. Okay, we'll talk about manipulation under this umbrella. And then another way we're going to make the systems more complex is by making them stochastic or uncertain. And we'll see how these tools can be generalized or not to handle stochastic systems. We'll talk about planning under uncertainty and other things like this. And then the last one, and it really depends if we get to it. Some terms we don't get to it because of we end up spending more time in the middle. The last one would be systems that are just really difficult to model, where it sort of doesn't make sense to even start by trying to write down F. So the dead fish might be a good example of that, right? So I could write down Navier-Stokes to describe the dynamics of the fish. But I'm not going to get very far in my control synthesis for that because F is just too complicated. It takes days to simulate, and so it's very hard to design a controller numerically for that. So we could take other approaches like trying to learn the control directly and do learning-based control. Okay, if we get to it, we'll end the term like that. Awesome. So last quick announcements. So the pace for the course will have problem sets. They'll be due on Tuesdays. They'll be due at noon, just so you're not running straight to lecture after you finish the problem set. We'll have office hours on Monday because of that, and also on Friday for you guys that just want to ask questions about the course or actually started your problem set before the weekend. Okay, so that's the plan. What else? Any other announcements like that?
Piazza.
Oh, we're going to use Piazza for the discussion forums.
It's linked from the edX.
And both the course notes and the discussion forums, everything is going to be linked off the website. Great. Looking forward to seeing you next time.